Our next derivation is a real fun one. It's what is the field at point P right here, which is on the axis of a uniformly charged ring of radius A. It's got radius A right there. Charge Q, total charge is Q, and we're trying to find the field a distance x away from the center, right here on the axis. So we can check our result by using one of these limits here. If x equals 0, what should the field be? In other words, if we're actually trying to find the field there, when we plug in x equals 0, what should we find? Well, it should add up to, well, if we go ahead and take a look at this, we can figure this one out conceptually. Here's dq. That will produce a field that way, but the opposite dq of it will produce a field that way. If we take a dq over here, it'll produce a field that way. If we take its opposite dq right there, it'll produce a field that way. We can play this game with every single point on here and realize that every point on this ring has a point directly opposite of it that is producing a field in the opposite direction. So these will all cancel. So in other words, the E field should be 0, should be E equals 0 at the center. And when we plug in our, get our final result, we'll check on that to see when x equals 0, if the field comes out to 0. So here's how we do this. What we want to do is we want to add up the field due to every single one of these dq's. What I'm going to do is I'm just going to draw right on here the dq, the field caused by dq right there. This, I'm going to call this dE. It's a little piece of the field, and it's going to be this dq right there, dq times k over r squared. What is r in this situation? Well, that's easy, because if this is a, the radius of the ring is a, and the distance away from the center is x, r has to be that, square root of x squared plus a squared. When we square that, we get dE, the little piece of the field caused by our dq, is just k dq over x squared plus a squared. Notice that I had a square root up here. I squared it, and the square root sign goes away. Well, that would be pretty easy, except notice that every single one of these dq's, and I'll do, for example, the one that's directly opposite it, this dq down here, that'll produce a field up this way. So, in fact, I've got it, when I integrate, I'm going to figure out E at point P is equal to the integral of k dq over r squared. I'm going to integrate over the whole ring, adding up all the fields due to every dq on the whole ring, but I'm going to have to include somehow this r hat. There's a vector aspect to this that I got to somehow account for. Well, it turns out that there is a trick that we use actually a lot when we have like a circular uniform situation like this, because I know every dq, like up here, has a dq that's right opposite it. Notice that every single dq on this thing, there's one right there, they all have a dq directly opposite to it. So a component of this is going to cancel. If I draw this as a sum of two vector components, let's go ahead and do that. I could draw this dE as a sum of the x component and the y component of this vector. I can draw it like that. Notice that this one has the same x component, the one on top has the same x component, but it has an opposite y component. So notice these y components will cancel. For every q and the q, every dq and the dq directly opposite it, for this dq and the one directly opposite, the y component cancels out. The only part that survives is the x component for every one. So all I need to do is figure out the x components of each of these fields caused by every single dq on here, and then I add up those x components, and then that's all I got to add up. So what I have to figure out next is the surviving, I'm going to put it in quotes here, surviving x component, which is not canceled. What does that equal? Well, it's the component of this. What I'm going to do is I'm going to call this angle theta. I'm going to call this angle theta. Same thing, right? So what is the x component of that? Well, the red arrow I've got here is just dE is going to equal k dq over x squared plus a squared times cosine of theta. That is the only component that survives. Well, what is cosine of theta for this theta? Notice cosine of theta is adjacent, that side, over hypotenuse, that side. Hey, that's really interesting. I can rewrite this as k dq over x squared plus a squared. Cosine of theta is going to be x adjacent over square root of x squared plus a squared. Okay, so I'm going to join these together. So this gives me the surviving x component is equal to, I'm going to call it dEx here, dEx equals k dq times x over, I'm going to write this as x squared plus a squared, and this is to the, that's to the 1 and that's to the 1/2, so this is to the 3/2. Okay, and I'm almost there. All I got to do now is I got to express this dq right here. Got to express that somehow in terms of x. Well, what we see, let's go back up to our drawing here, that it's got a total charge q, okay, but what are we going to do with this dq? Well, now you might say, well, I've got to use lambda because it's a linear charge density, but here's something that we can just kind of short circuit and shortcut this whole thing. Notice that every single thing here is a constant. Everything here is constant except for dq. So E, go back to black here, E is going to be the integral of kx dq over x squared plus a squared to the 3/2. And everything comes out except for is kx x squared plus a squared to the 3/2. That all comes out except for the integral of dq. Well, that makes it very simple because all this means is add up all the dq's. What do you get when you add up this dq, this dq, this dq, this dq, this dq, all of them, all the dq's? Add all those up. What do you get? Well, that's simple. That's just q. So the E field at P is equal to kx times q over x squared plus a squared to the 3/2. That is it. That is our field due to that ring. Notice we didn't even have to resort to expressing dq as a function of x because all we ended up with was the integral of dq, which means just add up all the dq's, you get q for that. I rewrote it to make it a little neater, but I want to make sure our equation is right. Again, we said that at x equals 0 at the center of the ring, the field should be 0. Let's see if that works out. Plug in x is 0. Here I get 0 over a cubed. So sure enough, this does work.